So, last time we looked at simplex and branch and bound, how we can use simplex to decide also linear integer problems. And branch and bound has the disadvantage that it branches. That means if you find a non-integer solution, then you have two subspaces to look at. So today we will look at the alternative approach, gomory cuts, which are also based on cutting down non-integer solutions from your real solution space, but it does not branch. So what is the basic idea? If you have used simplex as before, you can find real solutions, and if you find a non-integer valued solution, then we generate a new constraint such that it has the following two properties. First of all, if you add this new constraint, that it will cut down the solution that you found. First of all, so it does not contain, after cutting down the search space, the new subspace does not contain the found non-integer solution. And secondly, by this cut, we do not lose any integer solutions. So I go further one picture. If this was the solid lines were the original problem, then this space in between is the solution space in the reals. And you can see if I find this solution here, it is non-integer. For example, this line here would be a gomory cut, because using this line, I cut down the solution I found previously. I reduce the real solution set, but I do not cut away any integer solution. So while branch and bound would have taken either this half or this half for check, we have to branch. And by this gomory cut, we do not have to branch, we just reduce the search. And if the real search set is bounded, then similarly to branch and bound, we will terminate. And if not, it is also not complete. So, how can we generate such constraints, such gomory cuts? Just an intuition. If we have, for example, this constraint, 2x is less or equal 11. Then if I divide by 2, I just get 2x is less or equal 5.5. But if I want to have real valued solutions, then it is equivalent to less or equal 5. And such simplifications we can generate intuitively for such simple constraints, but of course if the constraints are becoming more complex, then it is not trivial to do it per hand, so we need some automated algorithms. And this is the gomory cuts, also called cutting planes. Gomory cuts are a certain cutting planes, certain type of cutting planes. But we will look only at that. So, we first look at an example, how to apply it, and then we will formalize it more generally. So assume we have three variables, x1, x2, and x3, and we have two lower bounds. x1 should be larger or equal 1, and x2 should be larger or equal 0.5. And now we solve first the relaxed problem. We use simplex, and assume that after solving simplex, we have this row in our tableau. x3 equals 0.5 x1 plus 2.5 x2. That means if I have here the tableau, then it has one row. I have here x3, and here I have x1 and x2, and the coefficients are 0.5 and 2.5. And I have a solution which assigns here the given values. So x3 has a non-integer value, x1 has an integer value, and x2 has also a non-integer value. And this set is a satisfying solution, so this will satisfy this equation. Okay, now what we can do is we can look at the difference of the equation gives me, this is equation 1, and by substituting the values gives me equation 2. And I can build the difference of these two. That means I substitute from equation 1, equation 2, and I get something like this. And now I can collect on the left-hand side the integer part of this difference. Basically, x3 should be integer, but it is not. So if I collect the integer part on the left-hand side by just adding up 0.75, then now I have an equation which on the left-hand side should be integer. So the right-hand side should be also an integer too in order to see an equation. But it is currently not. And I can use this piece of information to state some stronger statements. So again, here at the rightmost terms, they must be positive because I took here this one. This is the integer part of the value of x3. So x3 minus the integer part of its value will be positive. So I know that also the right-hand side will be positive. And actually larger than 0. So I know that this right-hand side will be in this case larger than 0. And since it should be additional an integer, I know that this is larger or equal 1. And this value is currently not, so I can substitute the values. So the value of x1 was in the solution 1, and the value of x2 was in the solution 0.5. So these terms in the current assignment are 0, and I have here a non-integer part because x3 was not integer. So what I know is that I have with the current assignment here something which is not an integer should be. So by putting this constraint, I will get something which is not satisfied by the current assignment, but should be satisfied by all assignments that lead to an integer solution. So if I add this inequation to my system, then I will cut down some solutions which are only real. So I do not cut down any integer valued solutions, but only real valued, which are at the corner of the currently find assignment. So we will first generalize this method, and then we will look at an example. So first we observe that in the example we had only lower bounds. We should also, of course also consider upper bounds, and also the coefficients can be negative or positive. So let us look at the general case. We will have an assignment, assume an assignment after solving the simplex such that at least one basic or original variable is fractional, and the non-basic variables. So here I have one row that this is fractional, the value, and in all the columns either I have additional variables, or if I have original variable, then its coefficient is an integer. These are assumptions which must be satisfied that I can apply the gomory cut, and why this is the case we will see if we have defined the method how to generate it. Okay, and one more constraint this we will discuss later. So assume that we have now, after simplex and assignments, And for this assignment, this assumption holds. So I have one row where the non-basic variable has a non-integer value, an original variable, and all the columns, if I have an original variable, then its coefficient is integer. And simplex returns me an assignment. So this row corresponds to an equation. xi is my basic variable with the non-integer value. And these are the additional variables, and these are the original variables. So this is the row defined by my simplex tableau. And we assume that the original variables, all values are, all coefficients are integer. So these are integer coefficients. Now what I can do is I know that this was an original variable, so this is an integer. The current value not, but it should be. These are also original variables. So this term here, since these are should be integer, and I also have assumed that the coefficients are integer, also this part should be an integer. So the only non-integer part is here in the current assignment. So what I do is I move this to the left-hand side, and I get xi minus this sum equals the sum over the additional variables, and I just denote this term by t. And t should be integer valued. Currently it is not under the current assignment, but this is our goal. So if it is integer valued, then I can also compute the current value for it, which will not be an integer. And I can just build the difference of these two equations, as before in the example. So I have the symbolic equation defined by the simplex, and I have the current assignment also giving me an equation. So this should be integer, but it's not. So I define the difference, t minus alpha of t. This left-hand side equals also the difference of the terms on the right-hand side minus their values. So far, so good. And now the basic problem with our assignment is that this value should be an integer, but it is not under the current assignment. So I will take from this part, from the current value, only the integer part. This I left on the left-hand side. And the non-integer part I move to the other side, to the right-hand side. This is this ft. And now, why I did this is because I want to get rid of this term. I know that the right-hand side should be integer, and I can just state that this should be an integer, and since ft is between 0 and 1, I even know that this sum should be also a fraction in order to be an integer. So now I would like to derive some conditions which must hold such that this term becomes an integer. We partition first the sum. In this, I go back at the slide. In this sum, there are additional variables, and I distinguish between if they have a lower bound, if they have an upper bound, and if these coefficients are positive or negative. And I use lower bound, the positive coefficient, for those terms where xj has a lower bound and the coefficient is positive, L minus where xj has a lower bound and the coefficient is negative, and similarly upper bound with positive and negative coefficients. And I group them. The terms in this sum group according to this. So what I will get is, this is the fractional part of the left-hand side, and then this sum here is split up into these 4 components where the variable has a lower or an upper bound and a positive or a negative coefficient. And now I make a case splitting. In the first case, two of the components, in the first case, I assume that this sum is larger than 0. I go back. This is this whole sum here. Case 1, I assume that it is larger than 0. And in case 2, I will assume that it is less or equal to 0. So if this sum is larger than 0, or perhaps it would have been even easier to assume that ft plus this sum is larger than 0. If it is larger than 0, since I know that the value is an integer, this will be also larger or equal to 1. And I just bring ft to the right-hand side, make some reformulations, and I get that since perhaps I have to go back a bit. So each of these sums are formulated such that if the index is in the lower bound, that means that this will be larger or equal to 0. Yeah, and if it has an upper bound, then this will be also larger or equal to 0. Because the values are, I had simplex solutions, so the values are always between the lower and upper bound. So each of these sums are larger or equal to 0 if the coefficients are positive, and less or equal to 0 if the coefficients are negative. So that's why I can, if I have some assumptions about the coefficients, I can tell that, for example, here the coefficients are positive and I have a lower bound, so these are also positive. So this whole sum, I know that it is larger or equal to 0. The same holds here. If I have upper bound minus the value, so this term is larger or equal to 0, and if I have negative coefficients, then I know that this sum here will be less or equal to 0. And if I take it minus, then I know that the sum is positive. So I collect the positive components. The other two components are negative. And if I collect these two positive components, then I know since, if I bring it into the other side, if I take the positive components and I will subtract something away, and this is larger or equal to 1 minus ft, then the positive components have to come up for the whole sum. That means I can imply that this equation here holds. And then I just reformulate by dividing 1 minus ft, and I get a final equation, this one. So it is nothing else than just making an assumption that a certain sum is non-negative, and I reformulate, making some implications, using the fact also that the sum is integer, and I get an inequation. And for the second case, I take the opposite assumption that this sum is less or equal to 0, and I can make similar implications. Namely, if it is again would have been easier to assume that ft plus this sum is less or equal to 0, then I can now, since it is less or equal to 0, I gather the negative components, and then these must be less or equal to 0, because if I add up something positive, this will not make it smaller. So the negative components must be less or equal to 0, and then again I can conclude a second inequation. So what we have is, we have two cases. First, I assumed that the sum is larger than 0. I got an inequation. Then I assume that the sum is less or equal to 0. I got another inequation. And now we bring them together as follows. I write down this sum here. This is the total sum in the original equation. And we observe that each of the components itself is non-negative. As I explained before, these terms are all non-negative. Then where I have positive coefficients, I add it up. Where I have negative coefficients, I make the difference. That means each of these components is larger or equal to 0, together with their sign. This is the first observation. All sum blocks are non-negative, and then I get two implications from case 1 and case 2. If case 1 holds, then I know that the blue ones are larger or equal to 1. And the red ones are larger or equal to 0. So the sum will be larger or equal to 1. In case 2, I know that the red sum is larger or equal to 1. This is what we derived. And I know that the blue ones are larger or equal to 0. So this inequation holds in all cases. Okay, perhaps how we have derived this inequation, you can look at it again at home. What I would like to do is a short example. So basically, this is the whole method. You have the simplex. Then if the solution is non-integer, then you search for a row which defines for a variable which should be integer, a non-integer value. Then you extract the equation, and you just define this inequation for this row and add it to your problem. And this will cut you down the current solution plus some more solutions, but no integer solution. Perhaps if you make an example, then we will see more. I have taken a simple one. We have 2x plus 2y is larger or equal to 1, and x is larger or equal to 0. Already here you can see that 2x plus 2y larger or equal to 1, we could strengthen it to larger or equal to 2. Because if x and y should be integer, then from 2x plus 2y larger or equal to 1, I would get by dividing 2 that x plus y larger or equal to 0.5. But if they are integer, then they are at least 1 in this case. But we do not do this because otherwise we will get directly the integer solution. So I bring it to the normal form, to the general form. Such that I can apply simplex. And I get the tableau. Okay. I have an initial solution in simplex. So first we have to solve simplex. Alpha of every variable is 0 initially. And I take the variable ordering x, y, s1, s2. So S1 is the first one violating its bounds, and X is the first one suited for pivoting. I pivot. S1 equals 2x plus 2y. If I pivot, I will get X equals 1/2 S1 minus y. So the new tableau will be (1/2 minus 1), and S2 equals S2 equals X from the first tableau, so the row will be the same. The values, the new values, S1 is put to its lower bound, 1. The value of y does not change, and I can compute according to the tableau that alpha of x will be 1/2, and alpha of S2 will be also 1/2. And I'm done because S1 satisfies its lower bound, S2 also, but my solution is not integer. And I search here for one row, namely for x. This should be integer, but its solution is not. So it defines me the inequation x equals 1/2 S1 minus y. And under the current solution, the value of x this is equation 2. So the value of x is 1/2 equals 1/2 times 1 minus 0. Actually, 1 times 0. This is the equation 1. This is the equation 2. And I build from here the fractional value is what I need. The fractional value of so what I need is also this alpha of x. The fractional value of alpha of x is 0. And what I do is, from 1, I get the value, so x minus the fractional part of x, this is 0, equals, I'll show you what I'm doing now. Here, yeah, we had the two equations. T equals the sum. This was the x equals the 1/2 S1 plus minus y. And then I compute also its values according to the current assignment. And what I'm doing now is make this equation, actually I only need the right-hand side. Yeah, what I want to have is this term, which should be an integer. So I build the difference in this equation. So I reformulate my equation here. I just minus the fractional value equals, the right-hand side was 1 alpha of x I'm sorry, just one moment, x minus alpha plus alpha minus alpha. Plus right-hand side with the value differences. So I just make 1 minus, yeah, I do the whole. So 1 minus 2. On the left-hand side is x minus alpha of x. On the right-hand side is 1/2 S1 minus y minus in equation to the value, the current value. Minus 1/2 the value of S1 minus the value of y. And now on the left-hand side I have something which is fractional, which is a non-integer now, and I would like to have only the integer part. So I take only the integer part. So on the right-hand side, I have to add up now plus alpha of x minus the integer part. So alpha of x minus the integer part of alpha of x plus the rest. And in the rest, I can pull it together to S1 minus alpha of S1 minus, or plus, minus, plus minus 1 y minus alpha of y. Okay, this is our equation. I just put in the values. This here is 0.5 because x was assigned the value 1/2. So its integer part is 0. And this is what is called ft in the equations. Ft is 0.5, and here I can add up alpha of S1 was 1, and alpha of y was 0. So, if I go back here, now we have everything what we need. We have this in equation. Here, this is the right-hand side that we have now. This is the right-hand side of our equation. We know that it is larger or equal 1, and we can apply now to this sum, apply now our rule which we was derived here. So, we collect I write it to a new slide. We have 0.5, this is our ft, plus, and this term is 0, so I have 1/2 S1 minus 1 oh sorry, and this I have to bring to the left because this is my original variable. I just write down this x minus alpha of x was 1/2, and this is 0. So on the left-hand side I have 0. On the right-hand side I have 0.5 plus 1/2 S1 minus 1 minus epsilon y. Okay, now I bring this to this side, x minus y, because it is an original variable. I forget it on the right-hand side. 0.5 plus 1/2 S1 minus 1. And I know now this term is to which I can apply my equation. And then I know that this is larger or equal 1. And if it is larger or equal 1, then I can write this in equation. So I have only the positive one. I have only one variable with a lower bound and the coefficient is positive. So I will coefficient divided by 1 minus this ft times the variable minus its value. So the coefficient is 0.5 divided by 1 minus ft times the variable minus its value, should be larger or equal 1. This is what my equation previously, which I derived, defines. And if I compute it, this is 1. So what I get is S1 larger or equal to. Okay, I go back to the previous slide. What we had here is a constraint, a lower bound on x1 is larger or equal 1. For the equation 2x plus 2y larger or equal 1. And now I got something stronger, and I'm nearly ready. I try to visualize it. If I have in equation 2x plus 2y equals S1, then I have, okay, 2x plus 2y larger or equal 1. From this I get that y is larger or equal minus x plus 1/2. This was my constraint. So this is something like this. This was my original constraint. And now we got the new constraint that S1 is larger or equal to. That means 2x plus 2y larger or equal to is the new constraint. And from 2x plus 2y larger or equal to, I get that y is larger or equal minus x plus 1. So the new constraint, we define a cut here. So the original search solution space was this, because x should be larger or equal to 0 plus this inequation should hold. And by using this cut, this part is cutted out, because this does not contain any integer solution. It will cut down the currently found solution, namely, I must check which one it was, 0 and 1/2. This was the old solution. This is cut it down by the new constraint, by the red constraint. And I have a new problem, and if I apply now simplex to this, then it is probable that we will find this point, which is integer. Okay, this was a bit fast, and I'm already a bit over the time. I would suggest that next time we will do one more example, and then we will look at another method for linear integer constraints, which is complete. So also this is not complete, but we will look at one which can solve all problems. Thank you.